so on. So these little squares here are 90-degree indicators. All right. So we're trying to find the orientation, the component of this intrinsic spin vector OS, right, along the z-dashed axis. So this is the component. The component is OR. Okay. All right. So OR is the component of this intrinsic spin vector OS along the direction of the z-dashed axis. In other words, OR. Right? OR is, now look, this point T here, if you draw a perpendicular to the x-dashed axis, it'll cross at point F. All right. Now, can you see? And you just probably can you see that the OR is equal in length to FQ? Right. It's just like two sides of the rectangle. You know, here, here, and here. They're all 90 degrees. Right? This is a rectangle. Okay. So OR and FQ are equal. Right. So OR equals FQ. This equals that in length. Right? But FQ, what is FQ? Here's FQ, it's this distance here, F to Q. So can you see that FQ is equal to FT minus QT? Does that seem fairly obvious? I'll say that again. FQ from here to here is equal to FT minus QT. I hope that's obvious. Alright, so write that down. So FQ equals FT minus QT. Alright. Right, now that's, what is FT? What's FT? FT. Is OT. Okay. This FT here is look at this triangle. Look at this triangle here. OFT, right? And we're trying to find this length. Well, we know this length, right? And we know. We know this angle. We know this angle here between OT and TF. We know this angle. Right? It's just theta. This angle here is theta. All right. We know this length. That's the hypotenuse. OT is the hypotenuse, and we're trying to find this length here. Well, this length FT is the cosine times OT. Follow that? FT, you think of this triangle, TOF, so OT is the hypotenuse of the right angle triangle. Here's your right angle here. This angle here is theta, right? So therefore this FT length is the hypotenuse times the cosine. So it'll be OT cos theta. There it is there. All right. Now what's QT? QT. Now this angle here between ST and SQ is theta. This angle here is theta. Right? And we want to know what's the length of QT. Well, ST here is the hypotenuse of the triangle TQS. Follow that? Alright? And we want the length QT. Well, QT is the sine theta times this hypotenuse, ST. So QT is ST sine theta. And we subtracted it, right? ST sine theta. Alright. You see what I mean? It's non-trivial, right? Unless you can find a smarter way. Okay, now what is OT? OT. Well, it's just the z component of S, right? This vector S. I'm using S as a point, as a point letter and as a vector. Maybe a bit confusing, but OT is just the component of S along the z-axis, right? So OT is just SZ. It's the component of your intrinsic spin, S, vector S, along the z-axis, SZ. That is your OT. Alright? Now similarly, ST here. What is ST? Well, it's ST is the same as let's call it Q. So ST is just the same as OQ, right? You just drop this vertical down to the x-axis. So ST is the same as OQ, and what's OQ? Well, it's the component of your S vector along the x-axis. Right? So rewrite ST as SX. Right? Now, a little bit of a trick. Now, I could have had this angle, I could have had Z dash like this way, right? To the right of the Z-axis. And instead of talking about theta, talk about minus theta. So, to get the expression in the textbook. So I just said, well, theta is arbitrary, so instead of going theta that way, how about theta that way, the other way? So make theta minus theta, just because, just convention. So plug in minus theta here and here, and you'll get, now cos of minus theta is just the same as cos of theta. But sine, sine of minus theta is minus sine theta. So then you get a double minus, so you end up getting this expression, right? Where this theta is now sort of that way. Follow that? Follow that logic? All right. There you have the component along the z dashed axis in terms of the component along the z-axis and along the x-axis. Okay? So you've now got this expression. All right. Now begins the quantum mechanics. So that's classical mechanics. We now use the correspondence principle. We assume, and you may say, well, why is the assumption valid? Well, the usual thing. It works. You test your hypothesis, that is, that you can use the classical and then convert it into a quantum mechanical equivalent simply by taking these physical quantities and making them operators. So here's your assumption, your hypothesis, that doing this, converting these physical quantities into operators, quantum mechanical operators. So we'll put a hat over them, and we assume that that's valid, and we justify doing that because of its consequences. We'll start with this now in quantum mechanics. We will derive all kinds of results. It has consequences. And if those results fit experimental data, then probably doing this is valid. Right? It's, the usual thing. We've done this kind of thing before. Right? Okay, so assume this is true. We have expressions for Sx hat and Sz hat. Right? Here they are here. We've done that earlier. Now the math is very simple because we're just talking 2 by 2 matrices now, right? So plug in S of z hat, put in this expression here, and an equivalent expression for Sx. Put that here, add them, and you will get this. I haven't even bothered to ask you to do it for homework. It's so trivial, right? You can just do it. You can see it visually that this is the case, right? Well, that's the end of the session. But what we'll do next? See, we now have a matrix. We have an operator for Sz dashed hat. Okay, we have an operator. And since it's so simple, it's just a 2 by 2 matrix, we can easily solve it for we can put this operator into an eigen equation and solve for the eigenvalues and the eigenfunctions, although in this context the eigenfunctions tend to be labelled eigenvectors, right? Because they're just two component, well, they're state vectors. They're a vector with 2 rows and 1 column. So we usually just call it column vectors, so just vector. So so we have this operator. We can put it into an eigen equation and solve for the eigenvectors and the eigenvalues. And interestingly, no matter what this theta is, when we come to actually to solve for the eigenvalues, we will keep getting plus or minus h bar over 2, as I was saying earlier. Right? But now we do it with the mathematics. It comes out of the mathematics. So next session I'll actually prove that no matter what theta is, your eigenvalues for the component of your intrinsic spin, your spin, along the z dashed axis will be plus theta h bar over 2 or minus h bar over 2. Right? No matter what theta is, which is interesting. So we'll do that next session.